Hi everyone, in this video today I am going to discuss about the proof of the trigonometric ratios of the compound angles by using the concept of polar coordinates. The formula of trigonometric ratio for the compound angles are cosine of a plus b. It has the formula cosines of a times the cosine of b, and here is plus, so here is negative, sine of a times sine of b. This is the formula of cosine of a plus b. A plus b is the compound angle. Here in this video we will prove these relations of the trigonometric ratio for the cosine in the compound angle. Here the a and the b are the angles, they are added together, so a plus b called as the compound angle. Similarly, we will prove here the formula of cos a minus b, which is the cosine of a times the cosines of b plus sine of a times sine of b. These are the two formula of the cosines of the compound angle. Similarly, here we will prove the formula of sine a plus b, which is sine a times cosines of b plus cosines of a times sine of b. This is the formula of sine a plus b. Similarly, the formula of sine a minus b will be here the negative sign. In this lesson, we will prove these all four relations of the trigonometric ratio for the compound angle. We already discussed about the polar coordinates. Here I am going to use the concept of the polar coordinate to prove these four relations by using the concept of polar coordinate of a point. Let's make a xy plane here, and the horizontal axis is x-axis, the vertical axis is y-axis, and the intersection is the origin. Taking origin as a center, let's make a circle of the radius. Here we construct a circle of, let's say, its radius is r unit. Here we construct a circle taking the origin as a center, and here we say the radius of the circle is a r. Now taking a point on the circumference of the circle, let's say this point name is a p, and now writing its coordinate is x comma y. This is the Cartesian coordinate for the point p, and let's say this line, inclined line, this radial vector, this is the radial vector, make an angle of a with positive x-axis. This is the positive x-axis. Here the radial vector OP makes an angle of a with positive x-axis in counterclockwise directions. So we can write the equivalent polar coordinate for the point P is the x is r cosine of the angle. Here the angle is a. Cosine of the angle, comma r sine of the angle. This is the polar equivalent of the point P. We already discussed how to convert the Cartesian coordinate into the polar coordinate. Here we just write the relation. Here the point P, x comma y, can be written as r cos a. Here the a is the argument, it is the n angle with respect to the positive x-axis, and the corresponding value of the y is r sine a. This is the polar representations for the point P. Here the angle A is formed, and let's suppose another point here. this is the point Q, which is at the same distance from the origin. This is the radius of the circle. This is also the R unit. This is because it is the radius of the circle, and uh, it makes an angle of, yeah, angle between the OP and the OQ is, let's say this angle is a angle B. The angle between the radial vector OP and the OQ, here we say the angle is B degree, and the line segment, the radial vector OQ makes an angle of A plus B with positive x-axis. Here the line segment OQ makes an angle of A plus B with positive x-axis. So its corresponding polar coordinates will be R cosine of angle. Angle is here A plus B with the positive x-axis, comma, R sine of that angle A plus B. Here we just write the coordinate of the point Q in the polar form. Here the argument is A plus B with respect to positive x-axis. So we take here A plus B, and this is the compound angle. Here we take the 2 points P and the Q on the circumference of the circle, and we join the points to the origin, and the radial vector is formed here, and we write the coordinates of the points P and the Q in the polar form here by using the relations. Now here we take the point P and Q. Now here taking another point, another extra point is a negative B. Negative B means moving the B unit uh, below the x-axis. So let's take another point here. Let's say it is R. It is, and the line segment which connects the O and the R is at a, let's say this is B degree below the positive x-axis. Here we take the third point R, which is at B degree below the positive x-axis. So the B will be negative B because it is below the positive x-axis. So and this length OR is the radius. So it has the measurement R here. We suppose the R is the radius. So the corresponding polar coordinates for the point R can be written as R cosine of the angle, and here the angle is negative B, comma, R sine of the angle. Here the angle is negative B. This is the corresponding polar coordinates for the point R, and this can be simplified as a R cosine of the negative angle is just cosine of the positive angle, comma, and the sine of the negative angle is negative of the sine of the angle. Here we simplified these relations, and we got here the polar equivalent, polar form of the point R also. Here we take the 3 points P, Q, and R, and we change the coordinates of the point P, Q, R in the polar form. And here the angle, let's say this is the point, yes, here this is this angle between the positive x-axis and the line OQ is angle, here the angle QOS is here A plus B. Here the angle QOS is A plus B. Similarly, angle here the angle POR is A plus B. They are the equal angles. The POR is also A plus B here. And the angles, the central angles are equal, so the chords, this implies the respective chords or respective arcs are equal. So the arc corresponding to that angle, it angle is the QP PR QPS. Here the arc corresponding to an angle QoS is QPS. This is R is equals to the arc corresponding to the angle POR, and the arc is PSR. They are equal. We have the theorem on the central angle of the circle. If the central angles are equal, then the corresponding arcs will be the same. So the corresponding chords will be the same, and the corresponding chords, with respect to the angle QoS is this chord QS. Let's join QS, the QS chord, and the another chord with respect to the angle POR is this chord PR, and they are also equal. Here we connect these 2 points and we formed a chord here. The chord, therefore the chord here, the QS is equals to the chord PR by the theorem of the relation between the central angle and the chords. So the chords are respective chords are equal. Now we can square this on the both side, squaring on both side. QS square is equals to the PR square. Here we square on the both side of this equation. Here the coordinates of the point, every point P, Q, R, S are known. So let's find out the distance between them. And here the S has the coordinate of, it is R unit away from the center, so R comma 0. It lies on the x-axis, so the coordinate is 0, R comma 0. Now using the distance formula, we can calculate the distance between the QS square and the distance between the PR square. Let's use the distance formula. Here the QS between the Q and S. Here I am going to use the distance formula. Q and S, using the distance formula Q and S. Here we use the distance formula x2 minus x1 square plus y2 minus y1 square. Here we remove the radical sign because it is square. And similarly, the distance between the point P and R, the distance between the point P and R can be calculated. And here R sine, this is very lengthy, R sine A minus here we just use the distance formula to calculate the distance between the point Q and S and the P and R. Let's simplify these relations. Here is a form. Here is a form like A plus B square. Now using the formula, this can be written as here we use the formula of the algebra A plus B square. This is very lengthy. We can skip the steps here. And this can be here also we can use the formula of A minus B whole square. cos A times cos B plus r square cosine square B plus here also we can use the formula. This is very lengthy and here r square sin square A plus 2 r square sin A times sin B plus r square sin square B. Here we just use the formula of algebra a plus b square and a minus b square. Let's simplify this. Here r square cos square, so here the terms are cancelled each others or not. The cos A times r square cos square B, there is no terms, and here let's take here the terms r square is common in each terms, so we can cancel it out the r square, and after taking the r squares we got the here cos square A plus B, and here is the form, very beautiful form here. With this first term, first term r square cos square A plus B, and this third term r square sin square A plus B gives the result 1, because we know the formula of sin square theta plus cos square theta gives 1. This is 1, and here and then minus 2 r square cosine of A plus B remains in the left hand side. Here the another things here, the r squares also present here. This r square is also here present. Let's take this r square here is equals to, here on the right hand side here is a form like r square cos square theta, and we can connect it with these terms, the result will be 1, and here also the same case, r square cos square B plus r square sin square B, 1, this 1 plus this 1 gives the 2 minus the remaining terms are 2 r square cos A times cos B plus 2 r square sin A times sin B. Or this can be further simplified rather. Here this is not 1, here we can take the r square as the common, this is r square, so here is also r square, we can take the r square as a common, and then this will be the formula 1, and here we can, here the r square, here r square 2 r square, and here the 2 r square present, so we can eliminate the 2 r square, and then here will be 1 minus cosine of A plus B is equals to, here the 2 r square will be cancelled out here, 1 minus cos A times cos B plus sin A times sin B. Here we just cancel out in this step the 2 r square which is present in each terms. Now let's simplify this one cancel out, and if we transpose this negative cos A plus B to the right hand side, then this will be positive cos A plus B, and transposing these terms on the left hand side, then cos A times cos B minus sin A times sin B. Here we simplify these expressions, this algebraic form, and then we finally got the value of the cos A plus B. The value of the cos A plus B is a cos A times cos B minus sin A times sin B. Here we just use the distance formula to calculate the distance between the 2 points, and we here simplify, then finally we got these relations. Here we prove the first part. Here the first part, the cos A plus B, the formula which is here proved. Similarly, for the relations cos A minus B, just replacing the plus B by negative B, just replacing positive B by negative B. If we replace the B as a negative B, then we got relations cos A times, this will be the negative B, B will be here replaced by the negative B, and the cos negative B gives cos B, and here the B is replaced by negative B, sine negative B gives minus sine B, and this will be plus sine A times sine B. If we prove the formula of cos A plus B, then we can easily prove the formula of cos A minus B just by replacing B by negative B. Similarly, the formula here we prove the formula of cos A plus B is the formula of cos A times cos B minus sin A times sin B. And we also prove that here the formula of the minus cos A minus B is the plus. Here we prove these two formula. Now the turn of sin A plus B. Sin A plus B. Now calculating the formula for sin A plus B using this relation. And for sin A plus B, we have the relation between the cosine and the sine. The sin A plus B, the formula of the sin A plus B can be written as, in terms of the cosine function, cos pi over 2, or it is 90 degree, minus the same angle, minus A plus B. This is the relation between the sine and cosine. The sine function can be written the 90 degree minus the angle. They are the complementary angles, so we can subtract it. Now, and this form can be written as cos pi over 2. Pi over 2 means 90 degree minus A. This is one angle minus B. Here we just arrange the angles, and here is a form like cos A minus B. Right? We can use the above formula here. If we use the above formula, then our expression we will get the formula of sin A times cosine B plus cosine A times sin B. Just by using the formula of here the two angles, and we prove the cosines of the compound angles, cosines for the compound angles. Then after using this formula, we got these expressions. Therefore, this is the value of the sin A plus B. Here we also got the relation for the sin A plus B is the sin A times cos B plus cos A times sin B. Similarly, for sin A minus B, just replacing B by negative B. If we replace B by the negative B, then the expression will be sin A times the cos negative B gives the cos B. If we replace B by negative B, then here will be the minus sin B. So this minus times plus gives negative cos A times sin B. Here to prove the formula of sin A plus A minus B, we use the relations of the formula of sin A plus B, just replacing the B by the negative B. Here we prove this formula also. So finally, in these relations, we prove all the trigonometric ratio formula for the compound angles, sine and cosine. Similarly, if we know the values of sine and cosine, then we can easily calculate the values for trigonometric ratio for the tangent and cotangent. And similarly, the second, we can calculate these relations after calculating this formula. Let's summarize this whole process. Here, in these lessons, we first make the circle on the xy plane, and then we locate the how many points here, the 4 points here, and we change the corresponding Cartesian coordinate into the polar coordinate, and then we use the distance formula. Here we use the geometrical relationship between the chords. These are the chords are equals here, and then we square on the both side, and then for finding the distance between the points we use the distance formula here, and then simplify, then we finally got the our required expressions. And similarly we proved the other relations by using the first relations. This is all about the proof of the compound angles for the trigonometric ratio. Please keep watching this channel. That's all for today. Thank you.